Okay, this is hour 2 for Physics 1C for September 24th, and right now we're going to be talking about the idea of electric current. This might be what people commonly refer to as electricity. I don't know. Up till now, the previous chapters, which is something like 4 chapters in this textbook, I believe, what we've been talking about would be referred to as electrostatics, where we discussed point charges and the fields they produce. We discussed the idea of electric potential and how it could be produced between 2 plates. And then we talked about capacitors and all this kind of stuff. But primarily what we were discussing were systems in which, at least for long periods of time, the charges are not moving. Like the example of a capacitor plate. Today's class, we began with talking about charges, building up on a capacitor plate. That process takes nanoseconds to occur. Okay, so while there is a small flow of charge in the case of throwing a switch and letting this occurs in like nanoseconds. The capacitor plates become charged, and once they're charged, we consider it kind of an electrostatic situation. And what we now like to talk about is what happens when I have some kind of a wire. Okay, so say I've got some piece of wire right here, and we kind of zoom in on it and say that piece of wire is connected to a battery of some kind, where because the battery has a positive side and a negative side, and let's pick some numbers right here. Let's say this is a 9-volt battery, and the positive terminal, let's just fix it at 9 volts, and the negative terminal, let's fix it at 0 volts. And let's say that it's connected with some kind of a wire like this, so that this piece of our wire, this is literally just going to be some kind of thick piece of wire right here. It could be for example copper wire maybe. And we'll make it so that the left end ends up being at 9 volts by connected to the positive side of a battery, and the right ends up being 0 volts. Right? What we know is that this is going to produce an electric field inside of our copper wire. And the direction of the electric field, which way does it go? Does it go from 9 to 0, or does it go from 0 to 9? What's the direction of the electric field in here? Should I put arrows going to the right, or should I put arrows going to the left? 9 to 0, exactly. So we know that there's electric field that's produced in this wire right here, right? It looks something like that. It points from left to right. And that electric field, in reality, exists in this portion of the wire. It exists in this portion of the wire here as well. And what it's going to do is it's going to create a force field within the wire that pushes charges, right? It's going to have the effect of taking any positive charge that you would find in here and putting a force on it so that it flows to the right. So positive charges in the wire down here would flow this way. Positive charges in the wire right here would flow this way. Simultaneously, if there were negative charges in the wire, since negative charges feel a force opposite to the direction of the electric field, the negative charges in the wire, assuming they're free to move, would move opposite to it. Okay? Inside of here, there might be some negative charges drifting off to the left. This type of flow of charges is what we call electric current. Okay? And we use the symbol I to represent electric current, and we say it's related to the rate at which those charges flow, and we call that dq/dt. Okay, electric current is a flow of charges that occurs due to a potential difference between 2 points, right? Delta V is like a potential difference. When you have a potential difference within a wire, it's going to cause a flow of charges, and we call that flow of charges electric current, and the symbol for electric current is I. Okay. I probably knew at one point in time why they called it I. I don't know now. Maybe for instantaneous current. I don't know. Maybe that's something that you guys can look up during this time while we're talking. But yeah, so you create this flow of charges, a flow of charges that basically can continue perhaps indefinitely until maybe the battery gets corroded and doesn't work anymore, as batteries tend to do, and at that time the flow would stop. This type of electrical current flow is happening in electrical wires that connect a power generation facility to your home. The current is flowing through whatever device you're talking to me on, your computer. Whenever you plug something into a wall, if you've got a wall socket, right? In a wall socket, you've got these 2 little slits, right? and then you've got a big slit in the bottom. One of those slits is positive, one of them is negative, and this one represents ground. It goes into the ground. We are going to talk a little bit about batteries work today, Ash, a little bit, but not in a lot of details, because the ways in which like physical batteries work is really more of a discussion for chemistry, but it doesn't mean we're going to shy away from talking about it. It is something that you well, you guys tell me, did anyone here, did y'all actually make batteries in your chemistry class? I mean, maybe in high school or something like that. Did anyone make a battery in high school? So we'll talk about batteries and like what's going on inside of them a little bit more later. But the point is, like, when you plug a device in your house, right? You plug something in. The devices you plug in, right? If you look at like go look at like a lamp cord or something like that, right? If you look at a lamp cord, you're going to see that it has this piece that you plug in to the wall, and that piece has two little prongs that plug in. But then the wires very commonly, if you look at it very closely, it very commonly has like two pieces to it, right? And those two pieces, they go and they connect up somehow, maybe into the base of your lamp or something like this. And here's the base, and then that lamp has maybe something like this, and you've got a light bulb that goes inside of here. And inside the light bulb, you might notice that there's little tiny wires that run up like this, depending on what kind of light bulb it is. But the thing is that you've got something that you can plug in, where one of these is going to end up being positive if you connect it into there. The other one's going to be being negative if you plug it into there. And within this thing, what happens when you plug this in is there's an electric field that's produced in these wires. One electric field going this way, and then on the return path, another electric field going this way. And it creates a closed loop along which the charges that are within the system can flow due to this field that's been created. And so you have little positive charges that are going to flow through here, flow up inside of here, and then interact with this, and then it'll cause the lamp to light up, right? But then they got to go somewhere. Okay, these charges, they can't just pump into the light. The charges have to flow into the lamp, and then they have to go back down the return path this way, creating a circuit, a flow, just like this right here, a circular flow of charges like this. And as long as that flow occurs, the lamp's going to work until you turn it off. What happens when you turn it on and off? Well, you open up your switch in some way so that the charges no longer can flow. Okay. All right, so some questions here, so I'll answer them. Jesus says, as I remember, you need a cathode and an anode and a salt bridge, and you have a battery. That's what you learned in chemistry. Yeah, that's right. You've got your battery. That's exactly right. You've got a positive side. You've got a negative side. It's basically two different solutions, right? You have a redox reaction that's occurring where there's either one side might have a piece of copper in it or something like that. It's something along this line. You've got like two solutions, one here and one here. One of them is probably something like, I don't know. This is where I'm going to start saying things that are just going to start sounding stupid, but I'll try to remember. One of the solutions is like copper sulfate probably, or something like that. And within the copper sulfate solution, you probably have some like piece of metal sticking inside of here. The other solution is going to be something like silver nitrate, maybe, or something like that. I really don't remember. If this sounds, what's silver nitrate look like? Is that nitrate? Does that look right? I don't know. But you've got a solution, right? And the solution has because it's a solution of this copper sulfate, it has free ions inside of it, right? And so then over here you're going to have your let's use black for silver. So you're going to have like a piece of metal here and a piece of metal here. And then you clamp them with little wires, but you also need to have one other piece that he mentioned, which is this salt bridge, which connects the two of them, right? There's like hey, look, there's a picture that Ash shared with us. It's probably way better than I could do. This one has copper 2 ions and hydrogen ions. Okay. I can copy and put this into this picture, right? Oops. Cancel. I don't know if that copied it. All right, let's see if I right-click it, it'll copy it. Yeah, copy. I almost deleted your message. Didn't mean to do that. Well, we'll just pull it up and we can have it right here to look at it. Yeah, something like this. Got a piece of copper, and I guess in this case that this is your salt bridge down here at the bottom, probably, that connects the two solutions. And in this case, one of them is platinum, and this one's copper. And so basically, what's happening is that this requires that gas is being pumped in here. I guess this is a little different from what I was thinking of. It's basically the idea, though. and you get this flow of charges here. Okay, so it's a chemical process occurring inside the battery. At the plates, I believe the plates are, it becomes negative, right? The plate becomes negative, and as a result, the copper ions will basically fall onto the plate. Yeah, and you get this flow of energy, and then a voltmeter could read out, for example, what the voltage is. Yeah. All right. So thanks for that. Anyway, so we'll take my picture out of here. It's just a bad picture. But the idea is, in some way, you have one plate that's going to be accepting electrons, one plate that's going to be giving up electrons. Over time, the plates will actually literally get metal plated on top of them. Yeah, but that's what's happening inside of a battery. Inside your home, something different's happening. There's power that's coming in through a power line, but it works in the same way. You get potential difference between 2 points, and then you get charges that are flowing around. Now, your next question was some of the charges are recycled. It's not so much that they're recycled, I guess. I mean, I guess you could think about it like that if you want to. It's more that just they don't go anywhere. They don't ever really leave the system, you know? So I guess in that sense, they're kind of recycled. Like in a fountain, or the water that flows out of the fountain flows down into a pool, and then you pick that water back up and you make it flow again and again and again. It's a lot like water flow in a fountain, really. You said this is a chemistry thing of why a battery has a limited life, because the charges were recycled. Wouldn't the battery work forever? No, it doesn't work forever, because as the battery operates, it develops corrosion and internal resistance that eventually makes it so that the terminal voltage is no longer 9 volts. So when you go buy a 9-volt battery, if you were to attach a voltmeter to a 9-volt battery and measure its voltage, you often would not get 9 volts. And the older the battery is, the more that voltage drops. And at some point in time, the battery just isn't going to be able to work anymore. That's why, if you use the batteries in your remote for your television, you have to replace them eventually. The batteries in any device, you have to replace them eventually. They don't last forever. They do tend to last a pretty long time though. Right? Okay, so we talk about electric current as a flow of charge. The faster the charges flow, the bigger the current's going to be. The unit that we use for electric current is the ampere. 1 ampere. And the short version of that would be amps. We usually just call them amps. Or 1A is equal to 1 coulomb passing through some piece of your conductor per second. And this is considered to be the more fundamental unit. This is considered to be, if we talk about fundamental units in science, we're talking about units that can't be written in terms of fundamental units, that can't be written in terms of other things. And in physics 1A, your fundamental units are the meter, the kilogram, and the second. And now we've learned of another fundamental unit, which is the ampere. We treat the ampere as being a fundamental unit instead of the coulomb, and then we just define, that a coulomb is equal to an amp second. Amp times second. 1 coulomb is an amp second. The reason why we do this, I believe, is because amps are much easier to measure than coulombs. Amps are very easy to measure by using something called an ammeter. Get very precise readings of current, of amps. Coulombs a little bit harder to measure. Okay. So this is an example of some fundamental units that we use in science, and the ampere is one of them. Okay. All right. So if electric current is defined as a flow of charge per second, and we want to understand something like physically at the molecular level of how this is happening, then we want to ask the question, how fast do the charges actually move? Right? Like, how fast do these charges actually move in the wire? Okay, if I told you that there was 10 amps of current running through here, and in another wire I say there's 20 amps of current, I think it's pretty safe to say that if they're the same kind of wire, the wire that has 20 amps, the charges are going to be moving twice as fast. Okay? But the current doesn't tell you how fast they move, as in it doesn't tell you what their velocity is, right? It doesn't tell you their velocity, right? So here what I'm talking about is velocity. So suppose we want to figure out what the velocity of these charges is. Okay. In order to do that, we're going to mention something real quick here. So in this diagram right here, let me see if I can move some things around and get this in a different location. In this little diagram right here, you have two different conductors. On the top, you have a conductor without an internal electric field. Okay? And below, what you have is the path of an electron without an electric field. Now, I've told you before that metals are kind of like a gas of electrons that are confined within the walls of the conductor. And the way that gases work, they're composed of molecules, like the air in the room that you're sitting in is composed of molecules of air, which include nitrogen and carbon dioxide and oxygen. And these individual molecules, they're kind of vibrating all over the place. They're rolling, they're twisting, they're zipping very quickly throughout the room. Okay, and sometimes they bounce off the wall, they jiggle, they do all kinds of things. But their motion is very erratic. It's very random. Okay, some of the molecules in the air in the room are moving to the right, some are moving to the left. Probably about half as many as move to the right, move to the left. What do I mean by that? Well, they're not all moving to the right. They probably are moving off at some angle, but they would each have some component parallel to the ground. They're not moving in straight lines. So this picture that I'm giving you right here is not an accurate picture of what's happening inside the wire. A better picture of what's happening inside the wire is like this blue line right here. Okay? As the electron moves throughout the wire, it interacts with the materials in the wire. What does it interact with? Well, what's inside the wire for the electron to interact with? Can you guys tell me? What is there inside the wire for the electron to interact with? There's charges. There's the conductor itself, right? So if I wanted to kind of draw in here a picture of what's inside of here, I would say that there's kind of this almost like lattice network of positive charges that exists inside of here, where at every point on this grid, there's a positive charge there, there's a positive charge there, there's a positive charge there, etc. Okay? Every one of those dots represents a positive charge. And as this negative electron tries to move through here, it's going to be attracted to that charge, and that attraction may cause it to, change its path. And it may start going this way. It may do something like this, right? It may zip this way, interact with a piece of the material, then it may go that way, interact with a piece of the material here, then it zips that way, and so on and so forth. It's bouncing around, effectively random, okay? It just, quite literally, the electron moves randomly. It doesn't mean that it's not being moved as a result of, randomly doesn't mean that there's not some order to it. It's just that each individual electron, if we were to try to account for every single one of them, they're all moving in such an erratic way that our best word to use for it is random, that it's similar to rolling dice, okay? It's similar to drawing a number out of a hat. It's similar to playing the lottery or something like that. If you want to figure out what any electron is doing, it's very random, okay? It's still caused by things. It's just that the total motion is random. Now, what happens when we actually place an electric field within the conductor? So suppose we put the positive end of a battery over here, put the negative end of a battery over here. We produce an electric field that's represented by this peak line right here, okay? What's the effect of that? Does that make it so that the electron just moves to the right? No, absolutely not. Think about, for example, the surface of the Earth, right? Near the surface of the Earth, there's a gravitational field that points down like this, right? Gravity points down like that near the surface of the Earth, right? If I throw a ball, well, first of all, if I just drop a ball, it will definitely fall along these gravitational field lines, right? But if I launch a ball with some velocity, it's gonna curve like this, okay? The trajectory that the ball goes along does not have to be parallel to the gravitational field. Just the acceleration has to be parallel to the gravitational field, right? But the trajectory itself is not necessarily going to travel along those field lines, right? The same thing is true here. The trajectory that the electron has is going to be simply altered from the random motion that it had before. You're going to add in a force. And that force is going to generally push the electron to the right. Now, what is shown right here is that these pink lines represent, now the electron's still moving randomly, but in the first motion, instead of going to here, it's a little bit to the right of where it was before. And then in the second motion, again, it's a little bit to the right of where it was before. And then here, again, it's a little bit to the right of where it was before. And these little additional rightward motions all add up until the electron has this kind of net displacement along the wire. So it's still jiggling around randomly in here. It's just that en masse, the electrons are kind of very, very slowly being pushed opposite to the direction of the electric field. Okay? Does that make sense? It's still random motion. Okay? It's not like all of them are just all being, swept aside like in a river. What would be an example of this? So think about like on a river, if you have a boat and the boat is just being gradually carried by the current, the boat moves in probably a straight line along a river, right? But what are the water molecules doing in the river? The water molecules in the river are bouncing around erratically, just like this, okay? Do they all flow to the right? Sure. Over time they do, but most of them are just jiggling around in place. All right. So that's the type of flow of charges that occur. It's very complicated. We're not going to go into a lot of details analyzing the individual motion of electrons, just so you can understand something like this. So the goal here is to figure out how fast they move. All right. And when we describe the velocity of something inside of one of these conductors, we use the phrase drift velocity. And that's what we want to calculate, is the drift velocity of these particles. This next picture is just for that. Now, within our wire, okay, I just make this smaller, I guess, probably. So within our wire, we're going to consider that the wire contains charge carriers, okay? What's important to understand is that when we describe the flow of those charge carriers, okay, we can either think of the charge carriers as being positive, as in this picture at the top right here, or we can think of the charge carriers within the wire as being negative. In the simple case of batteries connected to copper wires, the charge carriers are 100% going to be negative electrons, okay? But each of these things represents charge carriers, okay? Now, when we think about current, we define current as the direction of the flow of positive charges. But there is physically no difference between these two pictures here. Whether we consider the charges that are in the wires being negative and being pulled to the left, they still produce a current, what we call electrical current. It still points in the direction of positive charge flow, okay? So while we can talk about negative charges moving to the left, the same idea can be expressed with positive imaginary charges moving to the right, okay? We define the flow of positive charges to be current, electrical current, okay? Now, in order to describe how the drift velocity works, we're going to use a little picture like this right here. So in our picture, we've got a battery. It's connected to a light bulb, okay? And we take one section of our wire here. And for what we're going to do now, just to keep things relatively simple, we're going to use positive charges because it just makes it a little bit simpler, okay? So we're going to say that these positive charges, they're all drifting to the right with this velocity vd. Does this mean that every single one of them is moving to the right? Absolutely not. This picture is very misleading. The charges are not all moving to the right, okay? They're all doing stuff like this, right? But over time, they drift, right? They drift by some tiny amount, which is represented by the distance between these 2 points. And that tiny amount is going to be the drift velocity multiplied by the time interval that it took for the charge to go between these 2 points here. All right. So what we're going to do is we're going to say that as these charges flow to the right, they are going to pass through this cross-sectional area here, A. All right. And our question is going to be how much charge crosses the area A. Oops. In a time dt. So how much charge crosses the area A in a time dt? All right. So how much charge? dq. We're going to call it dq, the amount of charge that passes. So first of all, in order to know how much charge actually passes through, we would need to know something about how many free charge carriers there are within our system. Okay? We would need to know how, I can put a question right here. How much charge? This is going to be the amount of charge that crosses the area A in time dt. We need to know how tightly packed are my charges within here. Okay? And another way to say that would be how many, I'm going to say free. That's one thing we need to know. How many free charge carriers are there per unit volume? Okay, so I'm going to define a symbol. We're going to call it n. And n is going to be equal to the number of charge carriers divided by volume. So it's a kind of density, right? It's similar to density. Like density is mass over volume, right? Charge density would be like charge over volume. This is going to specifically be a number. The unit in the numerator is just going to be nothing, just quantity divided by volume. Okay. So what is this going to mean? This is going to mean that for this is where we can kind of rely a little bit on chemistry. You know, in chemistry, you talk about how like atoms can have free. Sorry, we were talking about ions, right, earlier. You put certain types of solutions together with water, and it causes the ions to split up. That's even the wrong way to think about it. Scratch that. All I'm trying to say is that when you think about atoms, the larger atoms, specifically metals that form like this, they can have the outermost electrons can be kind of weakly bound to the atom, which as a result makes it so that those atoms can kind of, not atoms, those electrons can basically flow kind of within a material, right? You've got these outermost electrons that are kind of lightly bound to your atoms, right? And in the case of something like copper, copper may give up something like maybe 2 electrons per atom, or maybe it gives up 1 electron per atom. And that electron becomes what we call a charge carrier, okay? Now it's an electron. Am I talking about oxidation state? Am I talking about oxidation state? I don't know the answer to that question. I don't think so. Maybe. I don't think so, though. I'm just talking about how the outer atoms within metals are loosely bound. The outer electrons in metals are loosely bound and can be free to kind of flow within the system. Now, certain metals may give up exactly 1 electron per atom. Other metals may give up 2 electrons per atom. Maybe there's some average. Maybe it's, I don't know. But there's going to be some free charge carriers, okay? That's what I'm talking about, is free charge carriers right here. And that's going to be something that's going to have to be kind of told to you, is like, how does each of these things behave? And we'll see that show up in a problem. But nonetheless, little n is going to represent the number of charge carriers per unit volume, okay? So I would argue that if I want to find the amount of charge dq, right, what I would need to do is I would have to take the number of charge carriers per unit volume. I would have to multiply by volume, right? And then I would also have to multiply by Q, where Q is going to represent the charge on an individual carrier. It could be the charge on a single electron, for example. But that, the charge on one carrier, multiplied by the number of charge carriers per unit volume, and then multiplied by volume, that should give me the amount of charge that actually passes across this area right here, dq. Does that seem reasonable? Okay, so what's this going to be then? We're going to leave Q as defined as just the charge of one carrier. Little n is, again, what it is. It's the number of charge carriers per unit volume. The volume will be the volume of this little slice right here, because we want to know the amount of charge that flows through in some time dt. The volume of that slice would be the area multiplied by this distance here, which is drift velocity times dt. and that's equal to the amount of charge that flows across that area in a given amount of time. So it's related to basically how densely packed the charges are, and how fast they're flowing, right? Because these charges are flowing, right? So the amount that flows is going to be related to the rate at which they flow. If VD, if the drift velocity is really high, then you're going to get a bunch of charges that flow past here, right? If the drift velocity is low, they're not going to flow as fast. What's going to control the drift velocity? The battery. The bigger the battery is, the bigger the current's going to be, and as a result, the bigger the drift velocity is going to be. Now, what we can do is we can take this dt and we can divide it under here, and we can say then that our definition of what current is, which was the rate at which the charges flow, is now going to be directly related to this concept of drift velocity. Like this. So this allows us to define what the drift velocity is as well as what the current is in terms of fundamental properties of our material. N is going to be a fundamental property of the metal itself. It's going to be different. It's going to be related to density. It's going to be related to some other things. Q is going to be probably related to the charge on an electron, because in reality, the charges that are flowing in here are negative charges. And then VD is the rate at which they flow. Okay, so the faster the drift velocity, the bigger the current, right? The bigger the area, the bigger the current. So we're going to do a problem to actually calculate drift velocity. But before we do that, I also wanted to define one other thing. Current density. Current density is basically the current divided by the area. This is actually a vector that we call J. And this vector J is given by Q in VD. The direction of the current density, it's quite literally just you take the current and you divide by the area. But the direction of the current density is going to be the same as the direction of the drift velocity. Okay, so we've defined some things. Now we want to actually do a calculation with this stuff. Before we do that, do y'all have any questions so far about these things that we've defined? No? So let's look at a problem. Okay, I think we can see everything. We just need to be able to see this equation. Yeah. Go up just a little bit. So the question says a 12 gauge copper wire. 12 gauge is refers to basically the kind of the size of it, how thick it is, the diameter, you might say. In a typical residential building, has a cross-sectional area of this. It carries a constant current of 10 amps. We want to calculate what the drift speed of the electrons in the wire are. And this is where, see, let me get back up here so we can actually see this piece. It carries a constant current of 10 amps. What is the drift speed? Assume that each copper atom contributes one free electron to the current, and that the density of copper is 8.92 grams per centimeter cubed. What I want you to try to do, and I'll give you guys like 4 or 5 minutes to try to do this, I want you to try to calculate this drift velocity based on the information given here. You'll have to use some knowledge from chemistry. You may need to look something up on the internet. Not the answer, but you may need to look some information about copper on the internet to do this. See if you can solve this problem. You will need to use Avogadro's number for this problem, yes, as well as something from the periodic table that you can probably figure out. So take some time and think about it. Molar mass, yeah, you'll need molar mass as well. Atoms per mole. Is that right? Grams per mole. Does it look right? You do not need to use this piece of information right here. 12 gauge. That's not... You don't need to worry about what that means right now. Oh, I guess that should give you the charge on an electron too. Is that enough time? Does anyone have an answer? I'll give you a minute or two more. Yeah, I'll give you guys more time. I don't know if that's the right answer, but it's pretty close, probably. Dash says 0.00223. It's the right order of magnitude. I don't know. I literally don't. I would work it out. It very well could be the right answer. At the very least, it's very close. If you'd told me that the answer was like 1,000,000 meters per second, I know is wrong. But I know that the answer is right about in that range of what you put. So, anybody else got an answer? So the same. Looks like yours is a factor of 10. Unless Ash didn't add a 0 by accident or something. Yours is a factor of 10 smaller. Tie, right? But some consistency there. All right, let's see what we get. So let's grab this equation right here. Copy that down here so we can work with this. Oops. So that's the. There we go. All right. Is there a way that I can like slow? No, I have to. It's right here. I'd have to go just like that. Okay. Okay. So there's a few things we have to calculate here, and we need to use a lot of things to do so. So we've got area, and that's given in meters squared. It's 23. 3.31 times 10 to the negative 6. The current is I. That's one of the things that shows up in our equation. We're given density of copper. Okay, that's our given information. The thing that we need to figure out here really is this quantity here, N. And we said that N represented the number of charge carriers per unit volume. They're telling us that each atom contributes 1 electron. So it's 1 electron per atom. And we can figure out the number of atoms that we have basically per gram, and we can eventually turn it into volume if we want to. So let's do that. So we need to figure out the number of charge carriers per unit volume. And we've got mass over volume right here. So it's going to have to come out of this, right? So what's the best way to do this? I guess, I don't know how you did it, but to figure out what N is, what I think the best way to do it is to just kind of set up kind of a conversion factor, dimensional analysis, whatever you want to call it. So you do 8.92 grams over centimeter cubed. And then this tells us grams per mole right here, right? So if I multiply by 1 over the molar mass, so I put 63.546 grams in 1 mole. But then we also know the number of atoms per mole. So if we write that one right here. So this is, let's just summarize. This is 1 over the molar mass multiplied by the density multiplied by Avogadro's number. Okay. This is, oh, whoops. That's an ugly looking 3. 10 to the 23 atoms divided by mole for 1 mole. Those will cancel the moles out. So we've got, what are we at now? We're at atoms per volume. That's pretty good. We want number of charges per volume, though. So we need one simple thing in here, which is each atom contributes 1 electron. So 1 electron per, so it's basically going to be 1 electron per atom. And then we probably want to get it into meters cubed, right? Because this is in meters squared. So centimeters cubed, if I want to convert that to meters cubed, what we would do is we put 1 meter down here, and then 1 centimeter up here, and then we would cube it. And I believe that should give us the units we want, right? Because if we look at everything cancels out, you've got the centimeters cubed is going to cancel out with centimeters cubed from here, atom and atom, mole and mole, gram and gram, and we're left with just number of electrons per meter cubed, which is what we want, right? So it's rho times 1 over m times the Avogadro's number, and then multiplied by some other things, right? These things, which are basically just equal to 1. Oh, and this isn't exactly right here, is it? Let me fix this. Sorry, this should be 100 centimeters in a meter. So that should give us what n is. Let's just calculate that, because it's, there's a lot of things there. Let's see what we get.
Okay, this divided by 63 point. Anyone have any questions while I'm calculating this? Okay, so we end up getting 8.45 times 10 to the 28. God, that seems like a huge number. And this is going to be charge carriers per unit volume, but I'm just going to say electrons. Electrons per meter cubed. That's our unit. Number of electrons per meter cubed. Put a little circle around that because it looks kind of weird. So the number of electrons per meter cubed, or the number of charge carriers per meter cubed. Okay, so now our goal is to find drift velocity. So let's start plugging things back into together then. So drift velocity, according to our equation, should be equal to the current divided by the charge on one carrier, which is going to be the electron charge, divided by the n that we just calculated, and divided by the area of the wire, the cross-sectional area of the wire. So we have 10 amps in the numerator. We've got the charge on a single electron, which is 1.6 times 10 to the negative 19 coulombs. This is a fundamental constant. The charge of an electron. N was this number right here. .45 times 10 to the 28 charges over meter cubed. So we'll just put over meters cubed, because it's really just a number of electrons. The electron is not a unit. And then times the cross-sectional area, 3.31. Okay. So your drift velocity, by calculating all of this, I'm guessing one of you must have been right. It's either the one that's -4, or it's the one that's -3. What do y'all get when you calculate that? -4. Okay. Meters per second. Of course, we could probably write this in a way. 10 to the -4 is kind of weird, right? But if we write this like this is like, in terms of millimeters per second, it's 0.223 millimeters per second. That is how fast or slowly that these charges actually move through the wire. It's extremely slow, right? It's extremely slow. Millimeters per second. Like, ants probably move faster than this, right? Certainly millipedes move faster than this. A fifth of a millimeter every second. If you think about it, it would take 5 seconds for this electron in a wire. So we're talking about little electrons traveling very slowly through these wires. It would take 5 seconds to move a millimeter. It would take 5,000 seconds, or what is 5,000 seconds? Divided by 60. It would take 83 minutes, or a little over an hour and 20 minutes, for an electron in this wire, this type of wire, to move 1 meter. Okay, just think about that. If you had an electron and it's over here, and you've got electrical current, and the current is going this way, so if the current goes that way, the electrons actually go off in this direction, right? If you had a 1 meter section, and it had the same cross-sectional area of this wire right here, it would literally take 1 hour and 20 minutes for the electron to cover the distance of a meter. Isn't that crazy? It would take 1 hour and 20 minutes just to move a meter. And if you think about this, like, in the following thing, if you're in a room and the lights are off, right, and you flip on a light switch, how long does it take for the light to turn on after you flip on the switch? It's like no time at all, right? It happens instantly. It's like instantly. And I can tell you that it occurs on the order of like a nanosecond. So there is a time, but it's so short that we can't even possibly imagine it, right? But nonetheless, somehow that same wire that connects this, that's in the switch behind your wall, that connects up to your light switch, inside of it, the electrons are moving just about this fast, just a few millimeters a second at the most. They're moving extremely slowly, and the reason why they're moving so slowly, it goes all the way back to what we said at the beginning. They keep interacting with the material. They keep hitting all the protons and the other electrons, and they hit the material.
they can't help but dissipate some of their energy to that material. So they move very, very slowly. But nonetheless, that slow motion, that gradual train of electrons slowly moving through this material is enough to light your room. It's enough to move power from the Hoover Dam to Southern California. You know what I mean? It doesn't matter that they're moving slowly. There's a massive amount of energy in moving all of those electrons. After all, look at that. There's 10 to the 28 electrons for every meter cubed. That is a huge amount of electrons contained within a meter. Now, a meter cubed is a huge volume. I'll give you that. But when you move those electrons by even a millimeter, you produce a massive amount of energy, and that's the energy of electricity that we use to kind of power our world. This is this slow, gradual train of electrons making their way through these wires. All right. I'll let you guys think about that. We'll take a break, and we'll start again at 8:15.